This conference will now be recorded.
Good afternoon.
Good afternoon, ma'am.
Ma'am.
Had your
Good
lunch?
afternoon, ma'am.
Good afternoon, ma'am.
No, ma'am.
ಒಟ್ಟಿಗೆ ಊಟ ಮಾಡೋದು ಅಂತನಾ? After
Um,
class,
in, yes, ma'am.
relaxingly you want to enjoy your food. Same here. Okay. I think there must be one new person joined. Any idea? I could see the new name in the group, so I was expecting that person here. So anyway, hope all of you joined. We started with new topic that is about the drug stability. So we could revise yesterday some of the the types of stability issues with respect to the API, which can be a chemical stability issues or can be a physical stability issues. So let's not waste time here. This was just a brief idea for you to make you understand that there will be a lot of stability issues which can disturb the life of the drug, okay, and which can happen during the processing or even it can happen during the storage conditions. So any part of the time. So it becomes easy, it becomes mandatory for us to understand how the degradation happen, okay, and so that we can overcome the problems. So in continuation with that, I also started discussing about the kinetics aspect of the degradation process. So degradation is nothing but a process which happens. So to understand the process, how and what speed it is happening, how fast it is happening. So to understand that, we depend on the kinetic. We try to understand the kinetic aspect of the same process. So degradation reaction is nothing but a reaction which is happening. So that reaction, how fast it is happening, we need to understand with respect to the chemical kinetics. So before we start with the chemical kinetics, we also should know some of the basic aspects. That's what I was just revising last time. So any kinetic equation is nothing but the chemical equation we write for any reaction happening in this way. And that reaction helps, and the equation whatever we write helps us to understand the what speed the kinetic reaction is happening, the speed at which. Why we are bothered about the speed at which the reaction is happening? Because that helps us to analyze the shelf life of the drug. With respect to pharmaceutical aspect, let us understand that mainly helps us to calculate the shelf life of the drug so that we can overcome that and we can improve the shelf life of the drug. And all the condition which is affecting the shelf life of the drug can also be understood. So all that will help us to finally come out with a dosage form with its shelf life. I mean, how you can improvise the shelf life is decided based on this kinetic reaction. So whenever we write this reaction, so there are certain terms we also understood yesterday, that the terms like A and B, depending on this equation I'm talking it as, it's not a standard equation. Okay, it's just only the representative equation for our understanding. So A and B are nothing but the number of molecules. A capital A is the reactant A and capital B is the reactant B, and M and N, hope you remember all, it is the product. Okay, and A, how many number of molecules are involved in the reaction, or the small b, how many number of molecules are involved, that is represented by AB. And finally, when you write an equation to get an idea about the rate process of this reaction, whatever you have written, it's been written. So we need to depend on a mathematical basic concept that is called differentiations. So any change happening to the reactant A with respect to time, or any change happening to B with respect to time, or M or the N, change is happening. What change is happening in this case? A amount is decreasing, or the B amount is decreasing, or M amount is increasing and N amount is increasing. That increase decrease is represented by this symbol, the sign, negative sign and the positive sign. This is the negative, indicates that the rate of change of the reactant A or its concentration is decreasing with respect to time. Same with the B also. So wherever you could see there might be a slight change in the alphabetical representation. C generally stands for the concentration. It's how you express it. Or even I can write D like capital A also, the amount. So it depends. So here it is the concentration of the A which is changing with respect to time. So negative sign, hope you understood now, indicates the decrease, and positive sign indicates the increase. So that's about the importance of writing the differential equation, which is the first step usually we need to write, so that further it is simplified to derive a final equation which can be used for the practical purpose. So this is how the beginning the differential equation was written, and to correlate with the initial amount of the reactants. Okay, then the differential equation can be correlated with the initial amount of the reactant this way, that is dCA by dt is equal to K into CA to the power of A. So this A, so this is one of the differential equation which was written for only the reactant A. Similarly, we can write it for the reactant B also. Fine. So if both the reactants we are planning to understand how in what speed it is decreasing, then we can combine both together also, like this in the final whatever you are seeing here at the last equations. Okay. So here the power A and B, or the instead of power, let me use the proper term exponent. The exponent A and B indicates the number of molecules which take part in the reactions. Depending on this number of molecules, the combination of the number of molecules, we can understand what is the order of reaction it is following. Zero order, first order, second order, all this is decided based on the number of molecules involved in the reaction, and which is nothing but the sum of the exponent value. So ultimately we write the final differential equation for both the reactants together like this. This is just an idea for you all to make you understand that how the kinetic equation is represented initially and how it is simplified further with the help of the differentiation equation and taken to one of the level. Okay, but still when I say use it for the practical purpose, when I ask you to take it ahead this equation for the practical purpose, it's not very comfortably you can use this equation. So that's when the further simplification goes on. So anyway, we'll understand slowly one by one with respect to each kinetic orders. So some of them we'll be discussing here, the zero order, first order kinetics, and the pseudo first order kinetics. See, all these kinetics things what we are discussing with respect to discussing in the class, no, as per your syllabus, it's all relevant to the pharmaceutical dosage form degradation stability aspects only. There's a lot to understand about this kinetics, chemical kinetics. We cannot go in detail. So only which are important generally, what kind of kinetic order does the degradation follows, only that part we are going to stress upon. So let's discuss about the first one here. So it's a zero order. See, till now I told you, if you remember, the exponent A and B in this equation, when you write this A and B in the form of exponent, this one, so indicates the order of reactions. So this order of reaction, actually what it helps us to, what message it gives us is, it refers to the way in which the concentration of the drug or reactants influence the rate of chemical reaction or process. How the concentration of the drug means it gives an information for me. How does the reactants, that is initial component, or in our case it's the drug, it's influencing the speed of the chemical reaction. So in case of zero order kinetics, so when I represent the drug A is getting degraded, okay, by the zero order kinetics, when I say it is zero order, so the order is zero, means there is no exponent. That means the reaction rate is independent of the initial concentration. Hope you understood. The reaction rate is independent of the rate of change of drug A, is independent of the initial concentration of the drug or the initial amount of the drug. That's why it is called as zero order kinetics. It's not influencing the speed at which the change is happening or the drug is degrading. Degrading is nothing but some change is happening, correct? Right? So the change, whatever the speed at which the change is happening, no, that is independent of the initial amount of the drug. So zero order, according to the zero order reaction, if the amount of the drug A is decreasing at a constant time interval t, then the rate of disappearance of the drug A is expressed as saying whatever the basic equation I made you understand. So if the drug A is decreasing at a constant time interval, means like 1 hour, 2 hours, 3 hours, whatever the time interval, say 3 time interval, then the rate of disappearance of the drug A, of course the drug A is disappearing because it is getting changed to something else. So the disappearance of the drug A, now it is expressed as a differential equation. That's when you write it as a K naught. And if you notice carefully, I have not written here the CA or the A because in the zero order kinetic, it is independent of the initial amount of the drug or initial concentration of the drug. Let me just take you back to the previous equation to make you understand better. So here I had written here K into Ca, means in this example, initially when we begin understanding the kinetic equation aspects, there I have written the Ca here. That means it is dependent on the initial concentration of the drug. So this is not a zero order equation representation. Okay, so it is a first order equation. So that I will tell again later. So for right now, a zero order equation is written like this. Zero order differential equation is written like this, where dA by dt is equal to K naught, and we are not writing A beside the K naught for the simple reason that the rate of change of amount of the drug A with respect to fixed time interval or the constant time interval is independent of the initial amount of the drug. That is the initial amount of the drugs. That's the reason we have not written the capital A beside K naught. So K naught represent the zero order rate constant. So K naught is the zero order rate constant and the unit of the same is mg per minute, that is mass per time. So I expect you guys to at least understand the basic aspects of the zero order kinetics and the first order kinetics. So zero order gives us information. What is the importance of order? It gives the information about the concentration. It is the way in which the concentration of the drug or reactant influences the rate of chemical reaction, influences the rate, that is dDA by dt, how it get influenced by the initial amount of the A. In zero order, the rate of change of drug A with respect to time interval is independent of the initial amount of the A. That's the reason we write the differential equation is equal to K naught, where K naught is the zero order constant. Hope you understood. So going ahead, so just understanding the differential equation will not fetch us any information because we need to convert that equation such that can be applicable practically. Ultimately, we actually we want to use that theoretical equation, whatever we derive, the mathematical equation, whatever we derive, no, that should be practically applicable. So to derive to a practical equation which can be applicable, so I convert this previous equation. The previous equation is what? This one, dA by dt is equal to K naught, is further integrated. So when I integrate that equation like this by reshuffling the equation where I have taken dt has been shifted to right side of the equation. So I try to understand the change of the drug, change happening to the drug A with respect to two time interval. What is happening from 0 hour to 12 hours, 0 hour to 6 hours, whatever. How the change is happening from this time interval. So differentiation equation just gives us that the change happening with respect to time. How that change is happening with respect to time is done with the help of the integration. So integration equation is generally integration concept is generally applied to understand the change happening between the two extreme points. Okay, and in our case, the two extreme points is like the time interval. What is changing with respect to time interval? The A is changing. That is, amount of the drug A is changing. So that's the reason we are writing that zero, from zero time interval to the time interval which we are measuring, or whatever time interval we are planning to measure. Same here, A naught is the initial amount and AT is the amount at which this particular time, whatever the amount we are measuring, that is called as the AT. So this is how the integration of this equation will be done. When we do this integration of this equation, we get a straight line equation. That is what the interesting part. Ultimately, we want an equation which is a straight line equation because a lot of advantages we get when we convert any equation to straight line equation. It's a linear kinetics, for example. So when a straight line is there, extrapolation becomes easy for us. I can extrapolate the data even though I don't have the data. A straight line when you draw, and I extrapolate from the y-axis, I touch the straight line and extrapolate to the x-axis, I'll get the x-axis value. So this is the advantage of the linear equation. So whatever this integration was, the integration after applying the integration is getting changed to a straight line equation, and this is the final straight line equation we are going to get. Nothing but y is equal to, this is y is equal to mx plus c. Hope you understood now. This is being integrated, converted to a straight line equation where this equation is nothing but equal to y is equal to mx plus c. Mx is this one, mx plus c. One second. Okay, so the straight line I was trying to write some technical problem, I'm not able to write here. So y is equal to y, this is 80 is equal to y is equal to mx is what, this one. M is slope, x is x-axis. So k naught is slope and t is the x-axis. So y is equal to mx plus c and a naught is equal to c. So advantage of this is what, when I plot a graph between the y, that is 80, versus x, that is t, I will get a straight line. Once I get a straight line, I can easily calculate k naught, that is the slope value. So slope is equal to k naught. Directly I can say slope is equal to k naught. Okay, so when we plot this graph, okay, so a naught represents the amount of the drug here, and k naught is the zero order kinetics. And you also should remember the unit used for the same. So not just the rate we need to calculate, we also should calculate the t half, the time taken for the drug to degrade to half of its content. It's called as the t half of the, that is half life, I can call it as. So that is the best term can be used for make you understand that t half represents the half life of the drug in with respect to the subject what we are learning. So T half in case of zero order kinetics is 0.5 into A naught divided by K naught. So this you have to remember because T half equation will change when we go with the first order kinetics. So according to the zero order kinetics, T half is equal to 0.5 into A naught by K naught. So look at very carefully if you observe, the T half is dependent on what, A naught. That indicates what? It depends on the T half of the drug degradation is dependent on the initial amount of the drug. Okay, so this is what the conclusion we give. So what is the unit of T half then? The T half unit is time. This is just the time, minutes or hour, however you express this. So this is what the zero order kinetic concept. So you have any doubt, want to clarify? So just understand in a simple way, I try to explain any kinetic reaction equation. Initially, it is written with the differential equation, okay, and then it is integrated and converted to a straight line equation. The advantage of converting into straight line equation because we can conveniently plot the graph, and practically when we measure the respective parameter, that is y-axis especially, x-axis is time, default x-axis will be time interval. So y-axis is the amount of the drug or the concentration of the drug. However, whatever it might be depends on the method what we follow. If I'm determining the amount, then it becomes amount. If I'm determining the concentration, it will be C. Okay, so it doesn't matter. So ultimately we'll have a straight line. Once we have a straight line, what is the advantage? I can determine the slope. So if I can determine the slope, how it is helpful for us? It is nothing but equal to k naught. So I can directly say, immediately calculating the slope, I say this is the k naught value. Okay. Now the t half is the next thing which we can calculate. Once the k naught we know, then I can easily calculate the t half by substituting this equation, whatever I just explained. Fine.
Yes, ma'am.
Okay. So I
Yes,
expect you to
ma'am.
write. So ultimately, we are converting depending on the differentiation concept and the integration concept, and we are deriving the straight line equation. And this straight line equation has a lot of advantage because that helps us to calculate many of the especially the parameter that is constant, rate constant. So once the rate constant is there, I can easily calculate the t half value. So let's understand some of the examples required for our pharmaceutics that is stability issues. So these are some of the examples I can right now quote it, which I have taken from the textbook. I think it is Latchman textbook. Okay, so that this topic you can refer both, and that I think I told you, Latchman as well as the Martin textbook. So both are good book for the referring. So combining together, you might find this information. So zero order, let us see what are the examples of the degradation which happens in the pharmaceutical aspects. The one is the degradation of the drug in the solution, especially the suspension. Okay. Next is the photochemical reaction, the dose drug which are photosensitive. Even that follows the zero order kinetics. And the next one is the color loss in multi-sulfur preparation. The color change which can happen, which happens due to the chemical reaction also, maybe color is changing, or maybe due to the photosensitivity also color is changing. Whatever. Any color change which indicates the stability issue can be understood by the zero order kinetic. This all follows the zero order kinetic. That's why I'm supposed to tell you. So degradation, some of the major examples which you need to remember is this reactions like degradation of the drug in the suspensions. Now you don't ask me what is suspensions. You should be knowing what is suspension. Next comes the photochemical reaction which follows zero order. Last is the color change or color loss, also is following the zero order. So to understand in detail, this is how the reaction can be represented for the suspension, the degradation reaction, where the solid drug particles which is suspended, it goes into solution. That is what the one step which you have to imagine, goes into solution immediately to the vicinity of it and gets degraded later on. Means directly a solid which is suspended will not degrade to the product, whatever the degradant product, but generally it goes into solution. The little amount of the drug goes into solution. We cannot expect all the solid to go into solution, then you don't call it as a suspension. But those solid amount which goes into solution, it actually get degraded, and that degradation, by chance if it is happening, this is following the zero order kinetics. So as the drug is degraded in solution, more drug goes into solution till solid A has reacted completely. This keeps on happening. If you don't stop, if you don't take care of this, the suspended particles keeps on degrading. That means it is losing its activity. If you are allowing it to happen without taking care of the problem, it goes on, it continues till you go. What happens at the end? You are going to lose the activity of the drug. Okay, and this is how the degradation step can be represented. So why are you calling it as zero order process, this suspension degradation, the drug particle in suspension? This reaction does not depend on the total concentration of the drug suspended. So it doesn't depend on the total concentration of the drug which is being suspended, but it is whatever the degradation is happening, it is mainly happening because of the drug which is gone into solution. So it is not depending on the initial amount of the drug. So zero order, if you revise, if you recollect, it's independent of the initial amount of the drug. That's the reason in case of suspension, that is degradation process, the drug degradation happens after entering into the solution, and whatever drug present in the solution form in the solution only will degrade. So it is not dependent on the initial amount of the drug. That's why it is called as zero order kinetics. It's following the zero order kinetics. So first example you need to remember is the degradation of the drug in the suspension follows the zero order kinetics. So when I want to do it practically, so what I do is, so this equation now you're well versed with. So when I'm writing C, it stands for the concentration A. Okay, so fine. However, I want either I can calculate the concentration, that is the concentration of the reacting material, which is constant, that is initial amount. It's the initial amount. So I can also represent the with respect to amount of A, reactant equation can be changed to dx. I can rechange the equation with respect to dx by dt. X indicates the amount reacting. If you just recollect back in the PP experiment, I think somewhere you would have done the stability, first order stability kinetics and the second order, if I'm not wrong, zero order. I am not because I never handled the physical pharmaceutics, so I am not very sure. But I remember it is there in your syllabus, in the UG syllabus, that there you would have used these equations. Means for the practical purpose, I'm determining the amount reacting. So somehow we are determining the amount reacting, and then I'm plotting that against the time interval. So this is how the graph looks. So the different lines indicates it can be the reaction which is carried out at different temperature. For example, line 1, line 2, and the line 3 are of the different temperatures. So when I carry out the stability study, which is following the zero order kinetics, then I can carry out that at the different temperature. That is, again, it depends on the temperature. So degradation may not happen at the room temperature. Degradation may be happening little above the room temperature. So you need to understand that. So we can change the temperature of the study procedure in the study procedure, and then carry out the estimation of the amount reacting. So then plot against the time interval. You get a straight line. Take the slope value of this line, and then you can substitute in the equation. So slope is directly equal to k, that is a zero order kinetics, and we substituted t half to get, substituted in this equation, get the t half. Okay, this is how actually the practically the experiment can be done. So C is the initial concentration here that you have to remember, and X is the amount reacting, how much amount is reacting. So practically we can calculate that amount reacting. So right now you don't worry about the practical aspect. I'm just giving you idea that we can determine the rate constant, that is degradation rate constant, zero order rate constant for the drug which is getting degraded when it is in the suspension form, when it is formulated into the suspension form. If at all it is degrading, it can be understood by applying zero order kinetics. So we can calculate the K value, we can calculate the T half, and we can decide what is its shelf life. Ultimately, we get an idea about the at what time the entire amount might get degraded. If, and depending on that, I'm going to decide my storage condition, okay, or the preparation condition. So another example is color stability. I told you change in the color. Okay. So practically, if I want you to imagine change in the color, you cannot just measure with the titration process or any other process. It has to be done with the help of the spectrometric analysis technique. So this is what you try to understand. This, if the degradation in case of suspension, it is the drug which is getting degraded. I can measure that drug. How will you measure that drug getting degraded? I need to depend on the analytical technique. Without analytical technique, I cannot quantify it, how much it is degrading. So I can depend on the UV, or I can depend on even the titrimetric method, whatever the option. Okay, but I need to have a technique, analytical technique by which I can estimate. Same with the color change. Visually, you may be seeing the color change. I can say immediately, okay, there is some stability issues there. Color is getting changed, but how much? How what is its rate of color change? That cannot be visually analyzed. So I need to depend on analytical method. Again, that is the UV, that is colorimetry method or spectrophotometric method. So color change is measured. The loss of color, whatever is happening, that can be measured at using the spectrometric analysis, that is spectrophotometer, setting the wavelength 500 micrometer. Okay, 500 nanometer, let it be, actually there's a mistake here. There's a mistake in the unit. 500 nanometer, and it follows. I'll just come back to this unit in the next class. I need to confirm, but as I'm understanding, there may be a mistake, I feel. So anyway, so particular wavelength will be set to measure that color change. So the intensity of the color, light color, little bright in color. So that how the whatever the word light, bright I'm using, or it is like very dark in color, whatever, that is called intensity. So intensity quantitatively you need to analyze that. So that's why we depend on the colorimetry technique, and at particular wavelength we observe the absorbance. That's what it is used. The value to be plotted in the graph is the absorbance. I cannot plot the concentration here. It's the physical property change, that is color is changing. So it's not the concentration, amount is not changing. So color is change in color is measured with the help of the absorbance value, and this absorbance value is plotted in the y-axis, and the x-axis, as I always said, in the stability aspect, x-axis always the time interval. So as you can see the different lines here, the different temperatures they are used to understand the change in the color, at what rate. As the temperature increases, the speed of the color change also will increase. And that how will you understand? By calculating the slope of this line. So you take the slope of this line, you can easily understand the rate K. So how fast the reaction is happening. So that's about the zero order kinetics, one of the some of the important examples. Even the photochemical reaction also we depend on some of the analytical technique. So whatever it might be, all these three examples you need to remember, which indicates the which follows the zero order kinetics. So to determine this degradation, we depend on the analytical technique. So ultimately, okay, I have an analytical technique. I determine the degradation happening. Ultimately, what I am supposed to do, the data, whatever I get, I need to plot it graphically. I need to represent the data graphically. Without help of graph, it is not easy for us to calculate the rate constant. So once the rate constant means the graphical approach, I can say it's one of the convenient approach. There might be alternative approach by which you can determine the K value, but the best method to calculate K value is the graphical representation. So alternative may be there based on just the equation we may calculate, but graphical gives a better picture. So as soon as you look at the graph, you can say something is decreasing and something is increasing. Okay, so just that about the zero order kinetics. The next one is the pseudo zero order kinetics. It's the zero, it depicts a zero order kinetics, but it may not actually a zero order kinetics. Okay, so let us look into the example which actually undergo the zero order kinetics. The solid state means solid as such, it's not in the suspension. Solid as such can degrade, of course, because of what? Because of the moisture present around it. Okay, because of the temperature, whatever it senses around it. So this solid state, many of the drug decompose in the presence of moisture which is surrounding it, according to the zero order, that is pseudo zero order reaction. Why we use the word pseudo zero order reaction? Because this solid drug particle actually is not in the form of suspension, but the moisture around it during the degradation, it gives an environment like almost depicting the suspension, because the moisture is surrounding. What is suspension? The dispersed particle in the continuous phase, right? So when the dispersed particle is in the continuous phase, the continuous phase is surrounding the dispersed particle. So continuous environment may be moisture in the middle, that is the water, aqueous environment in case of suspension. Here the moisture is surrounding the particle. That's why it is depicting almost like a suspension. That's why it's called a pseudo zero order reaction. So the system behaves like suspension, and because of the presence of excess solid drug, the first order reaction rate becomes pseudo zero order. Means the moisture present around it is less comparatively to that of the solid drug particle. But in case of suspension, the dispersed phase, that is the solvent phase, is much more than that of the dispersed phase. That's the difference. So the pseudo order is represented by K dash. So whenever we write equation, we should be very careful and identify that we need to designate the constants properly. I need to represent the rate constant properly. I cannot write it as a K naught dash, or if at all you write it as a K naught dash also, why that dash you should write? The K naught dash indicates pseudo zero order rate constant. And when you write K naught, you write it as represents zero order rate constants. So please mention the parameters. So don't just write, because it depends, varies from textbook to textbook. Here maybe you can see dx by dt. Some textbook I told it they might write dA by dt. Depending on what is that they're using from the beginning, so they will be continuing the same till the end of the chapter. So you have to always mention what X stands for or what K stands for and what T. Of course, T is the one which doesn't change. You cannot change in any textbook. It's always same in, that is T alphabet. It will not change. Any doubt you want to ask me? No doubt. All are alert.
Yes, ma'am.
Yes, ma'am.
Ashita.
Yes, ma'am. Yes, ma'am.
Yes, ma'am. Why dear? No voice from your side. It's raining outside.
No, ma'am.
No rain. You're in Bangalore, no?
Yes, ma'am. I'm in Bangalore only.
Weather is so cozy, no? From past
Yes.
2 to 3 days,
In Nagasandra, it's not raining now, ma'am.
but it's cloudy.
Yeah, it's cloudy.
That's what, no? What I am feeling, I'm expecting the same expression from your side. Means here also it's very cloudy.
Okay.
Okay, all are alert. So I just want to wake you up. So, okay, let's proceed with the next one. First order. So
Yes.
what is the difference between now zero order and the first order? First order, the reaction, the rate of change of drug, whatever is happening with respect to time, it depends on the initial amount of the drug. So that's why it is called as first order reaction. Correct? In the case of zero order, the rate of change of the drug is independent of the initial amount of the drug. Rate of change of drug with respect to time, whatever is happening, is if it is dependent on the initial amount, then you call it as a first order reaction. And example, aspirin hydrolysis. Since this is what the experiment you would have done in the physical pharmaceutics. So I just need to refer back and come back and explain in detail in the next class. I'll let you know in detail about this aspirin hydrolysis. So if it depends on the first power of the concentration of the single reactant, till now we are talking about single reactant. Okay, more the number of reactants, there is a chance, not chance, it is more complex. The equation becomes more and more complex. That much I can tell you right now. Till in the first order, we just assumed as a one reactant only because we are talking about drug degradation. So the drug is interacting with something, the second the reactant is negligible. So the drug is main for us. So it's a single reactant only we are talking. So that's why the equation, whatever I'm writing in a straight line equation, I'm making you understand the straight line equation. They're all the simple straight line equation. But as the number of reactant increases, if you want to really understand what is happening to its kinetic rate, then the more the equation becomes more and more complex. So let's not worry about it because it's not our requirement. So first order reaction is nothing but it depends on the first power of the concentration of the single reactant. It is exponent. I'm talking with respect to exponent. So single exponent. So other language, what I can say, the rate of reaction is directly proportional to the concentration of the reacting substance. So either I can say the reaction is dependent on the first power of the concentration of the single reactant. Why it is first power? It is the first reactant. And it is again a single reactant because another reactant is not, we are not considering, if at all it is there. For example, aspirin hydrolysis happens in the presence of moisture, water molecule, right? So we are not emphasizing much on the presence of the water molecules. So that's why we are telling the first reactant exponent is the, it depends on the first reactant exponent. That's why it's the first order reaction. The best way to understand is that this statement, the rate of reaction is directly proportional to the concentration of the reacting substance. This can be represented by this way. So I've just proceeded, differential equation was written. I avoided all that step. Now you know that initially we need to represent this. This is how the equation to be written first to represent the reaction happening. Once that is written, we need to write the differential equation. And once the differential equation is written, if I say differential equation, it is not dA by A, we write the differential equation. It is actually dA by dt is equal to K into A. Somehow I missed it, I think here. dA by dt is equal to the equation I missed it in between. dA by dt is equal to K into A. That is what the initial differential equation we are supposed to write, which indicates that rate of change of drug happening with respect to time is equal to K into capital A. If you are writing, please write down that dA by dt is equal to K into capital A. Once that equation is written, we need to rearrange that equation. Say A, whichever was in the right side, is brought into the bottom of this dA, and the t has been taken to the other side. Now when I integrate it, this equation, this is how the equation should be written. Again, now I am telling you again, integration why we do, to understand how the drug A is getting changed with respect to two time intervals. And when I integrate that, see, it's a first order kinetic equation. The equation is converted to this equation. Ln stands for, can anyone tell what Ln stands for? Soundarya KV. What Ln stands for? Soundarya KV is rated 50. Asha. What does Ln stand for? You can speak, Asha. Little louder. Tell me what does Ln stands for here in this equation. When I integrate this equation, it is converted to ln A is equal to minus kt plus ln A naught. What does Ln stand for? Anyone can answer.
Ma'am, logarithm.
It's logarithm, correct? Anybody can add up to that? Chandana?
Logarithm base, ma'am.
Base what? Base what? That is the thing. Base of what? Ashita, can you add?
Ma'am?
What does ln stands for? Somebody said it is logarithm. I said okay, correct. And somebody said to the base something. They abruptly stopped. Base of what? Of course, it's a logarithm representation. Base of what?
Mathematical equation.
Oh dear. So your foundation. That's what I'm checking. See, logarithm, log. At least heard about log, everyone. Yes, correct. So everyone heard about log. Log can be of the two types: common logarithm and the natural logarithm. Okay, so logarithm, common logarithm is represented by log to the base 10, and natural logarithm is represented by ln to the base e. Okay, so as soon as you write, just write it when you write ln, it's understood that it is to the base e. So when I write log, it understood it's to the base 10. Means like 10 to the power of 10, 10 to the power of 100. Okay, it's to the power, I mean, we are playing with the 10, multiples of 10. So that's the reason. Okay. So it's been, when I integrate this equation, you are going to get another Python equation, which is in the natural logarithmic form. If you just go back to the, what is the zero order, when we did the integration, if you remember, what we got here, when the equation was integrated, to get a directly very simple, straightforward equation, which is a Python equation this also. But there is no log, I mean natural log or the common log, fixed. Because the initial differential equation was different. It is independent of the k naught. That is initial amount. This was the initial equation for the zero order kinetic. But in case of first order kinetic, it is dA by dt is equal to K into capital A. So the A is coming because of one of the alphabet variable is coming in the right side of the equation. The entire equation is changed now. So when we integrate it, we get a natural log straight line equation. This is again a straight line equation. Y is equal to mx plus c. But we find it difficult to handle this equation or use this equation. If you are rather than handle, let me tell you can use this equation. Application of this equation is very difficult. So I convert that into the common logarithm. When you convert this natural logarithm to the common logarithm, the equation becomes again this is straight line equation, no doubt in that, but which can be conveniently used for practically. So log A is equal to minus Kt by 2.3 plus log A naught. So it was a conversion factor. That is 2.3 is the conversion factor. When I convert this ln to common logarithm, I need to divide that with the 2.3. Okay, and that's the reason the equation will be simplified to like this, which is again a straight line equation. So when I have this equation with me now, I can plot the graph. Okay, what all I can plot the graph? Y-axis is equal to log A, x-axis is equal to t, and what is the slope? Minus k by 2.3. So that's the advantage. As soon as I get the equation, I can say what will be the slope. Why are you bothered about slope so much? Because why we are so much keen on the slope? Because it is the one which gives us the k value. What is k in our case? It is rate constant. So the rate constant is one of the kinetic parameter which helps us to understand the rate process of the degradation. So that's the reason we always look into the value of k. So when we plot, don't worry about what I was plotted against what. Y-axis against x-axis. The x-axis default is the time interval, and the y-axis it can be whatever you would have measured during the degradation. That is a left out drag you would have measured, or the drag getting degraded you would have measured. Whatever you would have measured, you are putting that into the y-axis, and this is how the graph comes as a straight line and slope is equal to this one. You need to remember, in case of zero order, slope is equal to k naught. In case of first order, slope is equal to 2.3 by k. I don't want you guys to do any mistake with this simple basic concept. The slope is equal to 2.3 by k, and k unit is time inverse in this case. Okay, so there actually I didn't mention that it's mt per time. Zero order kinetics, it is mt per time. So k is the first order rate constant, and always remember the unit as a time inverse. So as soon as I get the slope value from this line, I substitute the slope is equal to, at the place of slope I'm substituting the value of the slope is equal to 2.3 I will write divided by k I will write, and I cross multiply. Okay, when I cross multiply, I'm going to get the answer by 2.3. So please do the correction. It is not 2.3 by, it is k by 2.3. Not correcting and the mistake. So slope is equal to k by 2.3. So 2.3 into slope value, you are going to get the k value. So once you have the k value, fine. So I can correlate something. See, as I determine the k value, I can conclude something. Higher the temperature, greater is the k value. Faster. Faster will be the reaction as the temperature. So what equation now missing is the T half. So T half is equal to, in the case of first order, 0.693 by K. In case of zero order, it is T half is equal to 0.5 into A naught divided by K. There is a lot of difference between the first order T half and the zero order T half. So T half is equal to, in case of first order is 0.693 by K. Zero order is 0.5 into, that is initial amount of the drug, that is A naught divided by K. So let me wind up here. If you want to clarify anything, you can clarify. Nothing? Okay then, let's meet in the next week. You can please revise and you can get back to me, as I said, anytime the WhatsApp group if you are not ready. Okay then?
Ma'am.
Bye.
Yes, ma'am. Thank you, ma'am.
Thank you, ma'am.
This conference will now be recorded. This conference will now be recorded.